OCR A, strong acids, strong bases, and pH. Using Chemistry Explained means that you write notes on paper or tablet. You control the pace of the lesson through pausing or replaying the slides. Most important, when prompted, complete the task, thinking the problem through, taking your time before you check against the correct answer and then move on. So there is the plan. We're going to start with Arrhenius acids and their reactions, run through Bronsted-Lowry, the pH of strong acids, the ionic product of water, the pH of strong alkali, and then the pH of mixtures of strong acids and alkalis. Acids are ionized by the action of water to release hydrogen ions into solution. That is the theory of acids that we put forward at GCSE and in Year 12 or AS OCR Chemistry. And that's usefully labelled as the Arrhenius theory. And in this theory, it is the hydrogen ion H+ that is responsible for acidic properties. So if we look at an acid such as hydrogen chloride dissolving in water to form hydrochloric acid, by this theory, H+ ions are released by the hydrogen chloride, and it's the presence of H+ ions that cause acidic property. Similarly, in the Arrhenius theory, alkali are ionized by the action of water to release hydroxide ions into solution. So if we take the hydrogen carbonate ion HCO3-, dissolve that as a solid, otherwise known as bicarbonate, into water, the interaction or the reaction of water with the hydrogen carbonate generates a hydroxide ion, and therefore we would say hydrogen carbonate is an alkali. And this is usefully, as I said, summarized as the Arrhenius theory. Later on in this lesson, we're going to replace that with the Bronsted-Lowry. So we can look at the reactions of acids using the Arrhenius theory. There are 4 types of reaction you are expected to work with at A level: the reaction of acids with metals, metal carbonates, metal oxides, and alkali. So if I give you the reactants, could you complete the balanced chemical equation, correctly identifying, of course, the products? Pause, come back to check your chemistry. Okay, so if we look at the first reaction, we get magnesium chloride and hydrogen. Copper chloride, carbon dioxide and water for the metal carbonate reaction. With the oxides, we get copper chloride and water, and similarly sodium hydroxide gives us sodium chloride and water. Now, of course, these substances are all known as salts, with the exception of the reaction of metals. These are all neutralizations because they form water. The reaction with metals is not a neutralization, but we see that there is a change in oxidation number. Magnesium here as an element has the oxidation number 0, and here as an ion has the oxidation number +2. Hydrogen in its compounds is +1. As an element it is 0. So this reaction is not a neutralization, but you would be expected to recognize it as a redox reaction. So we also need to analyze those chemical reactions in terms of ionic equations. The ionic equations highlights the role of the H+ ion. responsible for acidic properties in the Arrhenius theory. So if we look at the equations that we've used previously, magnesium and hydrochloric acid gives us magnesium chloride and hydrogen. If I list these substances in terms of their ionic makeup, we'll see that magnesium, metallic magnesium, does not dissolve in water, whereas hydrogen chloride, hydrochloric acid, separates or dissociates into free aqueous ions. So we have 2H plus and 2 chloride aqueous ions. On the product side, we've got an ionic magnesium chloride, which dissolves to release the free magnesium 2 plus ion and the chloride ion, or 2 of them. Hydrogen is a molecular gas. Now you'll see that we have on the left and the right hand side chloride ions. So chloride ions in effect do not change. They're known as spectator ions. So we're going to remove them from our overall ionic equation, which comes up here. So my overall ionic equation is simply magnesium plus 2 hydrogen ions forms magnesium 2 plus, or the free aqueous magnesium 2 plus ion, and hydrogen gas. Moving from a list of all the ions present to the ionic equation is achieved by removing the spectator ions. So if I give you the copper carbonate equation again, try to write the ionic equation for that reaction. Pause, complete the task, come back when you're ready. So revealing, we've got here the copper carbonate as a solid, does not dissolve, whereas as previously hydrogen chloride dissolves to release 2H plus ions and 2 chloride ions in solution. Copper chloride is an ionic salt, so that will dissolve to form free ions, copper 2 plus and 2 chloride ions. Carbon dioxide and water are both molecular. However, they have changed from being hydrogen ions on the left-hand side and part of the copper carbonate. So what we want is what has actually changed. Well, the only thing that has not changed, that's exactly the same, is or are the chloride ions. So we can cancel those out or remove those from the equation and call them spectator ions. Now if I then go to the ionic equation, we can see we've got copper carbonate as a solid. Well, that doesn't exist as a product, so that has changed. It's the source of the copper 2 plus ions and the carbon dioxide, and of course the oxygen for the water molecule. So there is the ionic equation, having removed the spectator ions. Then from your third equation, copper oxide and hydrochloric acid, pause and write the ionic equation for that. So assuming you are ready, I'm going to reveal the ionic equation. Again, the chloride ions are spectator ions, so everything else has changed. And then your last equation, sodium hydroxide and hydrochloric acid. If you would like to write the ionic equation for that. So assuming you are ready, I'm going to reveal. That simplifies to hydroxide ions and hydrogen ions forming molecular water. And that, of course, you may have seen at GCSE, if you did GCSE, as the ionic equation of neutralization. You should also be aware of the mono, di and tri-basicity vocabulary. So a monobasic acid is one that releases 1 mole of hydrogen ions into solution. So it's in other words, it's a 1-to-1 ratio. So 1 mole of hydrochloric acid releases 1 mole of hydrogen ions into solution. A dibasic acid, sulfuric acid, H2SO4, full ionization releases 2 moles of H+ ions into solution, and a tribasic acid such as phosphoric acid, well, 1 mole of phosphoric acid will release 3 moles of hydrogen ions into solution. So we have a 1 mole to 3 mole ratio, or 1 to 3 ratio. So that's important in various types of calculation, including pH, but also, of course, in titration. At A level, you need a more detailed theory of acid-base behavior, and that's provided by Bronsted-Lowry. So a Bronsted-Lowry acid-base theory involves the notion of equilibria, that is reversible reactions, and a definition involving the transfer of protons. So not that distant from Arrhenius, in that, of course, a hydrogen ion, H+, is a proton. So an acid is defined as a proton donor. A base, its opposite, is a proton acceptor. So if we can write a generalized equation for acid-base reactions, the acid, A for acid, contains a proton, so HA. B for base is a proton acceptor. What enables it to accept a proton is, of course, the lone pair of electrons. So the transfer of the proton from the acid, the proton donor, to the base, the proton acceptor, results in HB as the product and A- as the other product. So the HA loses a proton to become A-, and B, the base, accepts a proton to become HB. So if we look at a particular example, hydrogen chloride, hydrochloric acid and water, could you pause and write down the products of the proton transfer? I hope you've done that. Come back to check against mine. So water accepts a proton to become H3O+, the hydroxonium ion, and hydrogen chloride, HCl, has lost a proton or donated a proton, so it is now Cl-. So, of course, what's distinctive of the base is the presence of a lone pair of electrons, so that can form a dative covalent bond with a proton. In the two equations, we can see that a base may or may not have a negative charge. The crucial thing is that it has a lone pair of electrons able to form a dative covalent bond with the proton. Now, if the reaction is reversed, we can see that HB in the reverse direction is donating a proton to A-. So HB becomes B- in the reverse reaction, and A- accepts a proton to form HA. So in the forward reaction, going forward, we would say HA is the acid, and of course B- is the base. But in the reverse reaction, we would say HB is the acid, and A- is the base. So if we look at HA and A-, there is a relationship between them, and we define them as a conjugate acid-base pair. So HA donates a proton and itself forming A-, but A- can accept a proton to reform HA in a reversible reaction. So we refer to HA and A- as a conjugate acid-base pair. So if we look at water, we have a new term to define, which is amphoteric. So water is able to act as both a Bronsted-Lowry acid and as a Bronsted-Lowry base, depending on its pairing. So if we look at an example of it as a proton acceptor from the previous slide, we have hydrochloric acid or aqueous hydrogen chloride and water giving us our hydronium ion and chloride ion, and I think we identified these as being acid-base, conjugate acid-base pairs. So acid HCl acts as a proton donor to the base and forms the chloride ion. So the two circled are a conjugate acid-base pair because the chloride ion can accept a proton to move back to form hydrogen chloride. Now, water accepts a proton to form the hydronium ion, but the hydronium ion can donate a proton to leave the water molecule. So just as HCl and chloride are an acid-base pair, similarly water and the hydronium ion are also a conjugate acid-base pair. But we can see there that water, H2O, is acting as a proton acceptor. Now, water can also act as a proton donor if it is paired with, for example, ammonia. So here we can see that water, H2O, is donating a proton to ammonia to form the ammonium ion and leave behind the base hydroxide. So the acid water forms its conjugate base, and the base, OH-, the hydroxide ion, can accept a proton to reform water. So in red there are another conjugate acid-base pair. In this equation, ammonia, NH3, is accepting a proton to form the ammonium ion. So ammonia is acting as a base. But in the reverse reaction, the ammonium ion donates a proton to the hydroxide ion and reforms ammonia. So again, in blue we have a conjugate acid-base pair. So here are three problems. For each equation, identify the conjugate acid-base pairs. Pause, come back to check your answers when you're ready. So if you are now ready, equation 1, H2SO4 donates a proton, so it's the acid, to H2O, which therefore is the base, to form the hydrogen sulfate ion and the hydronium ion. In the reverse reaction, the hydronium ion is going to donate a proton to the hydrogen sulfate to reform water and sulfuric acid. So our pairing is between the acid and its conjugate base. So acid 1 and base 1 are a conjugate acid-base pair. Water is acting as a base. Hydronium ion is acting as the acid. They are the second acid-base conjugate pair. If you're ready, let's move on to the second one. Here, water accepts a proton to form the hydronium ion. Hydrogen sulfate donates that proton to form the sulfate ion. So we have an acid-base pair between water and the hydronium ion, and the sulfate and the hydrogen sulfate form the second conjugate acid-base pair. If we look at the third example, hydrogen chlorate 1 and the chlorate ion are an acid-base pair because the hydrogen chloride donates a proton to phenylamine. Phenylamine forms ammonium ion, which itself then can act as an acid, donating a proton to the chlorate 1 ion and reforming phenylamine. So base 2 and acid 2 are a pair, and acid 1 and base 1 are a conjugate acid-base pair. Defining and calculating the pH of strong acids. So pH is a logarithmic measure of solution acidity, which produces convenient numbers. Its definition is minus log to the base 10 of the concentration of hydrogen ions or hydronium ions. But for brevity, chemists normally just list the hydrogen ion. So applying that formula, could you calculate the pH of these two examples? The concentration of hydrogen ions at 0.01 moles per decimeter cubed and then at 0.001 mole per decimeter cubed. Come back to check your answer. Okay, so in the first instance we have a pH of 2, so we put in 0.01 into your calculator, having preset minus log to the base 10, comes out as 2. And of course 10 to the minus 3, put through the operation minus log to the base 10, gives you pH of 3. You'll notice that a 10-fold change in the concentration of hydrogen ions produces a 1 unit change in pH. But before we move on, you must make sure that you can put this number into your calculator and get that number out. Okay. Similarly, you must be able to put that into your calculator and obtain this as the pH. So we're going to start with calculating the pH of strong acids. We need to be able to relate the concentration of the strong acid to the concentration of hydrogen ions. And we do that by assuming that strong acids are fully ionized. That is, for 1 mole of nitric acid, we get, on dissociation, 1 mole of hydrogen ions in solution. And that is, of course, true for every monobasic acid, provided that it is a strong acid. So 1 mole of nitric acid releases 1 mole of hydrogen ions. So the concentration of nitric acid is the same as the concentration of hydrogen ions. Nitric acid is monobasic, nitric acid is a strong acid. So let's look at an example. How to calculate the pH of 0.1 mole per decimeter cubed hydrochloric acid. Hydrochloric acid is a strong acid, so the concentration of hydrochloric acid equals the concentration of hydrogen ions released and is therefore 0.1 moles per decimeter cubed. We plug that number into the formula minus log the concentration of H plus ions, so minus log 0.1. Calculator provides pH of 1. So now try these two problems. Pause and come back to check your answers. Okay, so if you are ready, we've got 0.2 mole per decimeter cubed nitric acid. Nitric acid is a strong acid. So the concentration of hydrogen ions will equal the concentration of nitric acid at 0.2. Plug that into the pH formula. Produces a pH of 0.7. Now if you're ready, I'll reveal the second solution, or if you need more time, pause and try again. But if you are ready, the concentration of H plus ions will equal the concentration of hydrochloric acid at a value of 2.0. So plug that into the pH definition. It comes up with a pH of minus 0.3. Yes, pH can have negative numbers. One use of known pH is to calculate the concentration of hydrogen ions in a solution. So if we take the example of a solution of pH 4, calculating the concentration of H+ ions in that solution. So we start with the definition of pH. We put in the value that is known. Now I'm going to take you through stepwise. You can't fail method. Move the negative sign over to the left hand side, so -4 is equal to log 10 of the concentration of hydrogen ions. And using your calculator, press shift, then log and enter -4. That will come out as a value of 1 times 10 to the -4. That is the concentration of hydrogen ions. So I'll just repeat to go from this step to the final solution. If you've got a Casio scientific, press shift and then log and enter -4. Press answer or equals, and that will give you 1 times 10 to the -4. Try this problem. Calculate the concentration of H+ ions in a solution of pH 13. Pause, come back with your answer. Okay, so here is the answer. 13 is equal to minus log concentration of H+. -13 is log to base 10 concentration of H+ in my very stepwise method. Shift log -13. 1 times 10 to the -13 is the answer. So let's look at how to calculate the effect of dilution on pH. Now the key idea here is to realize that dilution does not change the numbers of moles of acid or alkali present. You're simply changing the total volume by adding more water. So the first step is to calculate the numbers of moles of hydrogen ions in the initial volume. Then calculate the new volume after having added some more water after dilution. Then calculate the new concentration of hydrogen ions in terms of moles divided by the new volume. So that's the answer from 1 divided by the answer to 2, of course in decimeters cubed. Then calculate pH in the normal way using the pH definition. So let's look at an example. Calculate the pH of solution formed by adding 50 centimeters cubed of water to 250 centimeters cubed of 0.2 nitric acid, HNO3. Nitric acid is of course a strong acid. So we initially calculate the numbers of moles of H+. So the moles of H+ equals the moles of acid, and that of course is volume times concentration. So that gives us 0.05 moles of H+ ions. Step 2, calculate the new volume. Well, that's 250 plus 50, which is 300 centimeters cubed. Calculate the new concentration of H+ ions. Well, that's the numbers of moles divided by the new volume, but in decimeters cubed. So that gives me 0.1667 moles per decimeter cubed. That's the new concentration of hydrogen ions. Plug that into the pH formula, and we get, coming out of the calculator, the pH for that new solution formed. Here are a couple of problems for you to try. Pause, read the questions carefully, work your way through, and come back to check your answers when you are ready. Okay, so problem number 1, there are the steps. The numbers of moles is the volume times the concentration. The new volume is of course 250 plus 250 in decimeters cubed. The new concentration is moles divided by the new volume. Plug that into the pH definition, comes out as 1. If you are ready, I'm going to reveal the solution to problem 2. Again, those are the steps. The numbers of moles is 0.1, which is the volume times the concentration. The new volume is, of course, again 0.5 decimeters cubed. New concentration works out as 0.08. Plug that in, pH of 1.10. The ionic product of water. The ionic product of water is given the symbol K subscript W. Now we know that water undergoes an ionization to a very small extent, and that ionization is endothermic. That is, we are breaking covalent bonds as we go from molecular water to the hydrogen ion and the hydroxide ion in aqueous solution. So that is an equilibrium, so we can write an equilibrium constant. Kc is concentration of hydrogen ions times the concentration of hydroxide ions, the right hand side, divided by the concentration of water, the left hand side. However, as the concentration of water is virtually unchanged, that is, this equilibrium lies almost entirely to the left, we can simplify the Kc expression into Kw, the ionic product of water, which is equal to the concentration of hydrogen ions times the concentration of hydroxide ions. So if we know the pH of pure water at 25 Celsius, we're able to calculate a value for Kw. Knowing the pH is 7, we can calculate the concentration of H+ ions at 25 is 1 times 10 to the minus 7. And as we can see that the numbers of hydrogen ions is the same as the numbers of hydroxide ions, we can also say that the concentration of hydroxide ions is 1 times 10 to the minus 7. Plugging that into Kw, which on the previous slide we showed was concentration of H+ times concentration of hydroxide ions, gives us 1 times 10 to the minus 7 times 1 times 10 to the minus 7, which of course is 1 times 10 to the minus 14, and our unit of course is moles squared decimeters to the minus 6. So that is the value, and it's always the value of Kw at 25 Celsius. The pH of strong alkali. So let's look at how to calculate the pH of a strong alkali. And we will need to use the value of Kw. So, for example, to calculate the pH of 0.1 mole per decimeter cubed solution of sodium hydroxide. Now, sodium hydroxide is a strong alkali. We can assume that the dissociation of a strong alkali is complete. So we can assume that the concentration of hydroxide ions is the same as the original concentration of sodium hydroxide. So 0.1 mole per decimeter cubed sodium hydroxide translates into a hydroxide ion concentration of 0.1 moles per decimeter cubed. However, that does not give us access to the pH value. To do that, we need the concentration of hydrogen ions. So we're going to go via Kw. We write down Kw and its value, 1 times 10 to the minus 14, is equal to the concentration of hydrogen ions times the concentration of hydroxide ions, and we know the concentration of hydroxide ions. Then if we substitute in the value of the concentration of hydroxide ions, like so, we can rearrange and solve for the concentration of hydrogen ions. So rearranging gives us the concentration of hydrogen ions at 1 times 10 to the minus 13. We then put that value into the pH definition to produce a pH of 13, which is a pH you will recognize as likely for a 0.1 mole per decimeter cubed solution of a strong alkali sodium hydroxide. Let's move on to giving you a problem straight away. Calculate the pH of a 0.5 mole per decimeter cubed solution of sodium hydroxide. Pause, calculate the pH, come back to check the answer and method. Okay, so the first thing we do is use the idea of the full dissociation of the strong alkali sodium hydroxide to give us the concentration of hydroxide ions, 0.5 decimeters cubed, moles per decimeter cubed, exactly the same as the original concentration of sodium hydroxide. We then write out Kw and its value at 25, substitute in the value of hydroxide, which gives us this, solve for the value of H+, put that value into minus log to the base 10, and we get a pH value of 13.7. Now, if we move to a problem involving a group 2 hydroxide, still a strong alkali, barium hydroxide, we'll see that the ratio between barium hydroxide and the moles of hydroxide ions is no longer 1:1 as with sodium hydroxide, but is 1:2. So 1 mole of barium hydroxide would produce 2 moles of hydroxide ions. So you need to take that into account when you try and calculate the pH of 0.3 mole per decimeter cubed barium hydroxide. Pause, see if you can come up with the right answer, come back to check. Okay, so our concentration of hydroxide ions will be twice the concentration of the barium hydroxide, so it works out as 0.6 moles per decimeter cubed. We then write out Kw, substitute in the value of hydroxide ions, or the concentration of hydroxide ions, solve for the concentration of hydrogen, and achieve the pH. Of course, the problem can be reversed. What is the concentration of a solution of sodium hydroxide of pH 13.2? Pause, see if you can solve the problem yourself. Come back to check against my answer. Okay, hopefully you're ready. So if the pH is 13.2, from that I can achieve the concentration of hydrogen ions. From that, via Kw, I can achieve the concentration of hydroxide ions. So if I write out Kw, substitute in the value of the hydrogen ions, 6.31 times 10 to the minus 14, rearrange and achieve the value of the hydroxide ion concentration. So I brought the concentration of hydrogen ions down to divide the value of Kw. Comes out as 0.158 moles per decimeter cubed. Well, because sodium hydroxide is monobasic, the concentration of hydroxide ions equals the concentration of sodium hydroxide. It's a strong alkali. So therefore my concentration of sodium hydroxide is the same as the concentration of hydroxide ions, 0.158 moles per decimeter cubed. Our last section, calculating the pH of mixtures of strong acids and alkalis. The key to this type of calculation is to find the numbers of moles of excess acid or excess alkali and the new volume. So here you'll be mixing a volume of acid and a volume of alkali, so there'll be a new volume. There'll be an excess of either acid or alkali. So the first step is to calculate the initial numbers of moles of hydrogen ions. That'll be volume times concentration. Then calculate the initial numbers of moles of hydroxide ions, again volume times concentration. Deduce or calculate the moles of hydroxide ions or hydrogen ions that are remaining after reaction. That is the excess. Calculate the new total volume. Calculate the resulting concentration of hydrogen ions, and then put that concentration of hydrogen ions into the pH definition to achieve the pH. So if I model one calculation, then I'll set you a problem on the next page. So calculate the pH of the solution formed when 200 centimeters cubed of 0.1 sulfuric acid is added to 100 centimeters cubed of 0.3 sodium hydroxide. So the moles of hydrogen ions, concentration times volume times 2. Sulfuric acid is dibasic. 0.1 is the concentration of sulfuric acid. 0.2 is the volume of sulfuric acid. And for every 1 mole of sulfuric acid, we get 2 moles of hydrogen ions. So our moles of hydrogen ions is 0.04. The moles of hydroxide ions, 0.1 times 0.3 comes to 0.03 moles. The excess hydrogen ions is the numbers of moles of hydrogen ions minus the moles of hydroxide ions, because of course hydrogen and hydroxide ions react on a 1-to-1 ratio. So we've got 0.01 moles of hydrogen ions remaining. That is an excess of 0.01 moles. What is the new total volume? 200 plus 100, 300 centimeters cubed. Work out the new concentration, that is the numbers of moles of hydrogen ions in excess divided by the new volume in decimeters cubed, comes to 0.033 moles per decimeter cubed. Put that concentration into the pH definition to achieve a pH of 1.48. Okay, so here is your problem. Calculate the pH of the solution formed when 200 centimeters cubed of 0.1 nitric acid is monobasic, is added to 100 centimeters cubed of 0.3 sodium hydroxide. Show that the pH of the resulting solution is 12.5. Pause, take your time, work your way through to achieve a pH of 12.5. Come back to check on my methods when you are ready. I've set out the full process so you can save time if you wish, but I'll go through step by step. So I've calculated the moles of hydrogen ions at 0.02. I've calculated the moles of hydroxide ions at 0.03. We have an excess of hydroxide ions at 0.01 moles. The new total volume is of course 300 or 0.3. So the resulting concentration of hydroxide ions is 0.033 moles per decimeter cubed. However, we need to access the concentration of hydrogen ions to achieve pH. So using Kw at 1 times 10 to the minus 14, I solve for the concentration of H plus at 3 times 10 to the minus 13. Put that into the pH definition, comes out as 12.5. So for my final slide, just the obvious statement that to consolidate you need to practice, you need to find problems from whatever source you have available to you, but those sources which have comprehensive answers are the best. So attempt the problems, check your answers. Move on when you are being consistently accurate and complete in your answers. Choose the next topic that you think for you is the one you need to focus on.